Now we reach the last part of the tutorial on exploiting engineering tools to produce specialized and highly performant systems. The third and the final idea we're going to mention in this tutorial is on lowering costing factors. Asymptotic runtime improvements are certainly desirable, but their successful implementation in practice is not a given. The database researchers uses a toolbox of clever techniques to bring otherwise computationally hard problems into the realm of the possible. So far, we only tapped into some of them. In particular, we looked into specialization for workload and data. And here the goal is to generate code specific to the query batch and the dataset, and generate code that has a good cache locality for the whole data path. The second aspect we looked into would be sharing low-level data access, in particular access to each relation. If you have a high workload of aggregates, we would like all of them to share just one pass over large relations. And also parallelization. Here we mostly looked at multi-core parallelization and considered both task and domain parallelism. In the remaining of this tutorial, I would like to highlight our effort on IFAQ, on iterative functional aggregate queries. The goal here is to design one DSL, one domain-specific language, to express hybrid machine learning and database workloads and to automatically optimize such workloads. IFAQ consists of functional aggregate queries as building blocks, which is a formalism that expresses computation in databases, linear algebra, AI, and logic, and has been introduced in PODS 2016 by Hung and others. Now, we consider relations here as dictionaries or maps. We also allow for conditionals via Kronecker deltas and some product computation over these dictionaries. We also allow iteration constructs for stateful computation over collection elements, and we also allow to construct nested dictionaries. IFAQ provides a rich pipeline of transformation steps that are aimed at optimizing together the feature extraction query and the subsequent learning task. IFAQ program, which is the input to this transformation steps, could express, for instance, an optimization algorithm such as gradient descent or the Descartes algorithm for decision trees. Then the program is subject to a series of high-level optimizations that could, for instance, do loop scheduling, factorization of code, static memorization, code motion, many other PL optimization techniques. After that, we specialize the code to the schema of the input data. Then we identify and extract aggregates from the program. We perform aggregate pushdown and fusion, and by doing so, we also achieve the sharing across the aggregates. Eventually, we look into relations, and we see relations as tries organized to match the order of join attributes. And then finally, we generate code that would minimize the number of operations, taking into account the try organization of these relations. And this shows in performance. We show in this plot the relative speed up of our code optimizations relative to our unoptimized code that performs the same task. And in this case, the task is the computation of the covariance matrix for linear regression. And as you can see here, just specializing the code can have staggering performance improvements with a factor of 8 times for retailer and even more for Favorita and Yelp, but not so much for TPC DS. If we also add sharing of scans of relations for the various aggregates, we get a further speed up of about 2x over the original speed up. And then with parallelization, we get even more.